Now let's look at the last example problem for this topic. It's also for meeting the middle. The problem is about the maximum subset sum. So here's the problem statement. We're given a set of n integers where n is at most 40. Each of the integers can be quite large. So here, let's say up to 10 to the 12. And the question asks us to find out the maximum subset sum that is less than or equal to target S. So here is an example. So suppose we are given this set of 6 integers and our target is 42. Then the maximum subset sum that is less than or equal to S is 41. So 41 can be obtained by using these 4 elements. So they add up to 41. And we cannot get 42 because for 38, we will need a 4 to get to 42. And for 34, we need an 8, so we can't make an 8. So there's no way to get to 42. So 41 is the best we can achieve. So obviously the problem can be solved by brute force by enumerating through our subset and compute its sum and see which one is the closest to S. But this will not be fast enough if n is 40 because 2 to the 4. We need essentially 2 to the n times n, so that's not going to be fast enough. And if the n integers are small, then all achievable subset sum can be computed using dynamic programming. And we can do that because if they are small, then the maximum achievable sum is limited. So then we can try to compute whether for each value it's achievable or not. So for example, if the maximum total sum is 10 to the 6, then we can solve it fairly fast using dynamic programming. But here the numbers are too large. So in general, this problem is this is a NP hard problem, NP complete problem. So we can't, if the number are large and there's no other structure within the problem, then it is going to be very hard. We don't really know any algorithm other than those are more or less quadratic, more or less exponential. But when n is 40, n is not that large. And we can use the meet in the middle technique to solve this problem by computing half of the set, computing things about half of the set, and then store it, and then we can look up that from the stored result efficiently. So essentially, we can take a square root of the time. Instead of doing 2 to the n, we can do in 2 to the n over 2, and that turns out to be efficient enough for when n is 40. So more specifically, what we can do is we can split the set of integer into 2 subsets, a and b. Let's say a has the first half and b has the second. Really, how to divide it doesn't really matter. We can just arbitrarily split them. And then we compute all the possible subset sum of integers in A, and then we store it in some data structure. I think we need to do array when we do this nearest thing. We sort it, and then these will use 2 to the n over 2 memory, and we pay this memory cost to get overall speed up. Then we enumerate through all the subset of B, and then for each subset sum, then we know what value in A will get to a value that is less than our target. Then we can do binary search on this array X to find the value that's below the target. So to make the sum below the target, and then we can record whether that is a better solution. And one thing I want to say is to enumerate all subset of an n element set. One way to do it is we just enumerate through all integers from 0 to 2 to the n minus 1. And then we interpret every number in here as representing a subset. And every bit of that number is indicate whether a particular element is included or not. So if the zeroth bit, if the lowest bit is 1, then that means the first element is included. If the first bit is 0, then the least significant bit is 0, then we mean that the first element is not included. So we can then the loop over all the subset can be done very easily by just looping through all the integers. So I think this problem illustrates meet in the middle. We're processing half of our data and store the intermediate result, and then when we process the other half, we can quickly look up. We don't need to doing any we don't need to repeatedly searching through the first half again. So that's all for this topic.